So this looks like question 1 for this kinetics assignment, and it's taken straight out of your textbook. Example 20A.2, so the method of initial rates. We briefly went over this in class a bit, and basically it gives you the data, and it already shows you up here what your graphs in Excel are basically going to have to look like. If I was you, I wouldn't actually spend too much time looking at this specifically. Even something as simple as this one has the log of I, but it says plus 5. So this plus 5 is, they're shifting the axis of their graph. So you're almost better off just to go ahead and make your own graph and follow the process that will become more obvious as you pick away at this. So what I'm going to do is, we know that it's argon and iodine. So let me just take you through this a little bit, how this is going to look. So let me turn this a bit. So how does this work? Well, they're basically saying that the rate is going to equal your rate constant, and they really are just estimating that they're hoping to find that the order in I is going to be some whole number, and they usually always start out with simpler examples, and the other one is what? Argon to the B. So what they're going to do is they're going to say, look, we could, and I think the first data starts out saying, what if these are initial rates, so as soon as they go to, and that's what the naught is there for, that signifies that these are initial rates. So we're going to move argon over here. Some people call this the isolation method, and what they're supposed to do, although in this question it's going to prove to you that you don't necessarily have to, you normally try to pick something like this and make it into a large excess, so that when the initial rate, and I guess this now gets a naught, it's almost like argon concentration is a constant. So they're going to call this K prime, right? And we've isolated out this. So the plan is you take the log of both sides, and you can see how you'll get log of K prime. And when you log this one, the A will come down in front, and you'll get log of the initial iodine concentrations. So this is basically what you're supposed to graph. And what you're going to notice is this, and which quadrant you're going to be in, I believe it's going to look kind of like that. So it should be a straight line. So the slope of this graph is going to equal A, right? The log of what's K prime is that, is going to be your y-intercept. So you're supposed to plot the log on the y-axis, if you will, right? Log of the initial rates. And on your x-axis, it's the log of I naught. And so basically put, you're supposed to, and if we look back here, you're going to have what's called, let's see if I can sort of piggyback this together here. Right. So notice, part A is when your argon concentration is 1 millimole per liter, and here's A. So you're given the concentration of the argon, but these are the rates, and that's the concentration of I. So notice how we just said we are supposed to plot the log of the rate versus the log of I. So you would take the log of these rates right here, the log of I. So these would be your x-axis in log form. And for part A, these will be the log of these initial rates. So you'll plot the log of this line versus the log of this numbers, right? So let's say and then of course you're going to end up with 3 of these graphs, one for each of the different concentrations of argon, right? So you're going to get three log of rates versus log of I concentrations. Don't forget that's times 10 to the minus 5. So you plot that, and what you'll have, for example, so you'll have the log of the rate for part A, and then you'll have the log of the initial concentrations, and there was what, 4 of them? So from part A, you have the matching log of that. So you're going to graph it, and you're going to get a straight line. So let's say your first one, part A, what I'm getting on that is Excel says it's y equals 1.999 x plus 6.937. So obviously this is your value A, the exponent. So it's going to be second order for that. This is going to be the log of K prime. So obviously what you could do is, working on this constant, you could put this side to that, right? But the interesting thing is, to get K prime, we know that it is equal to K times the concentration of argon to the B. So remember how we noticed that right here? We still don't know what B is yet. So if all I've done is graph the log of the rates versus the log of the iodine concentrations, and even if I got parts A, B, and C 3 lines, I'm going to confirm that A, right, is 2. The log of K prime, we have it, but we're going to have to wait till we finish graphing the other stuff so that we find out what B is. Then we'll come back here, knowing the concentration for part A, right? The concentration of argon for part A, the book claims, is 1 times 10 to the minus 3 moles per liter. And once we find out B, you'll be able to solve for K. And I think what you're going to find out, the concentration of argon is 1 times 10 to the minus 3 raised to the B, which we're going to find out in a moment is 1. So this will let you solve once you come back, but in real life, in a real question on your test or something like that, you are going to be able to solve for this. So I'm getting a number that comes out to 8.65 times 10 to the 9th. And you can figure out the units of what it has to be. So for part B and for part C, you'll have 3 of these lines, and you'll get 3 of these answers for K, and then you can, at that point, report the average of K for A, B, and C. When you move on to the next amount of data, we're going to go the other way with it. We're going to say we could have had, at this point, because we already did that, we're going to find out that A for this turned out to be a 2, right? And then argon to the B. We're going to search for that one. We have to prove it. So we're going to come up with a new, call it K prime prime, using some sort of initial rates. K prime prime, argon, B. So now we have to take the log of the rates, which will get log of K prime prime, plus B log knots, like that. And yet again, you will see it's going to be a straight line, just like the other one was similarly. It's going to look like that. Log of K prime, probably the intercept, the slope will equal B. So you have to graph the log of the rates versus the log of the concentration of these. So now when you look at it, you realize you have to go down, right? Because when you go from A to B to C, say you only have 3 data points going down. For part A, you have the concentration of argon is 1 millimolar. This is the reaction rate for it. Then when you go to 5 millimoles, this is the rate right here. Then you go to 10 millimoles, this is the rate. So you're going to take the log for this graph of this number. That's your log of the concentration. So that this will be your y-axis. This will be the log of this number will be your x-axis. Then you move to this one. You go log of this number y-axis versus the log of 5 millimolar. And then this number, take the log of it versus the log of 10 millimolar. So you see how now you're going down. These are your rates going down, matching these three concentrations in log form, and that gives you your next graph. But you see how you're going to be able to do 4 different graphs. And this will be the concentration of the iodine as you do it. So you're going to take the log. So you're going to say something like when the concentration of iodine was 1 times 10 to the minus 5th, I'm going to take the log of the rate versus the log of the argon concentrations. These logs were, take the log of 1 times 10 to the minus 3. The next one was when you went to 5 times 10 to the minus 3. Then it's the log of 10 times 10 to the minus 3. Those are your concentrations of the argon. And then you're going to go down the row of data for the logs of the rates to match it. You'll get the same thing here, and you'll get one of those. I think it's the first one, but I could be wrong. I'm just picking one here. I don't know if it's the first or the last, but one of the 4 straight lines you're going to get, I get 0.9996x minus 0.0616. Obviously that looks like b, the slope is equal to 1. This is k prime prime, and that would be log of k prime prime equals negative 0.0616. So k prime prime will equal 10 to the negative 0.0616, but k prime prime is equal to k times the iodine concentration, and we already know it's squared from part 2. So for this one, k is going to equal 10 to the, and we know that this, if I gotta double check and make sure this is the right one here. Where are we? Nope, not that one. Well, you'd have to make sure that this one matches the concentration of the one you're doing, right? I'm not 100% sure which one. So let me just look. I believe this is the first one. If that's true, again, stress this. I don't have time to go over it, but obviously you're going to see going down, you're going to have 1, 2, 3, 4 different lines, and each one corresponds to these concentrations. I think that what I just showed was the straight line for this concentration, but you can see it for yourself. Now, maybe I mixed it up. You'll know right away if it's the right one or not when you do it. So I'm just going to show you an example. If the concentration was indeed that one, you got to square it, right? And the calculation for that, I could check it right now. Second function to that, 0.0616 negative divided by 1 to the exponent of 5 negative squared equals, yep. So you get 8.67 times 10 to the 9th, right? You'll have 4 of these lines for this one. You can average your Ks, etc., and you're off to the races. So folks, the whole point of this exercise, and this is the other thing, I need to see you hand in your Excel graph that duplicates what you already see in the book. You show all of your work. I need to see, for instance, this one is finding B, and you get this is my data sets for the 4 graphs. You need to hand this in as well, right? And show your work. So that should handle it for that one. Be forewarned, one of your exam questions could conceivably be a question just like this.